This video covers Chapter 22, Inference about a Population Proportion. So what we're going to cover in this chapter are an introduction to our sample proportion, we call this p hat, large sample confidence intervals for a proportion, how to choose a sample size, how to conduct a significance test for a proportion, and plus four confidence intervals for a proportion. So let's get started. So the statistic that estimates the population proportion P is the sample proportion P hat, and P hat equals the number of successes in a sample over the total number of individuals in a sample. Now, success doesn't actually mean like success, like pass, fail. It could be like, oh, I want to know how many freshmen are at this university. So to be successful would be to be a freshman out of the total population of the university. And to conduct a sampling distribution with sample proportion, you have to draw a simple random sample of size n from a large population. You let p hat be the number of successes in that sample out of our sample size. The mean of the sampling distribution of proportions is p, our population proportion. And our standard deviation for this, the formula is a little bit different, so pay attention. It is the square root of p times 1 minus p over n. And as the sample size increases, the sampling distribution of p hat becomes approximately normal. So that is, for a large sample size, p hat has the normal approximation of p as its mean, and then the square root, the standard deviation being p minus 1p divided by n, and then you take the square root. So let's look at maybe like a visualization of this. So let's draw a simple random sample of size n from a large population that contains p proportion of successes. So we'll let p hat be our sample proportion of successes. So I've got our large population. I'm taking my samples and calculating the p hat of those n size samples. And those proportions, those sample proportions, are going to fit a normal distribution where our mean is p and our standard deviation is given by this formula right here. So how do I conduct a confidence interval? So first thing we need to note is that the standard deviation of p hat depends on the parameter p, a value which we don't know. So we can estimate our standard deviation with the standard error of p. So remember, standard error before, when we were working with means, was the standard deviation divided by the square root of n. Now our standard error is p hat times 1 minus p hat over the square root of n, okay? So if I'm going to conduct a large sample confidence interval for a population proportion p, with some characteristic, my approximate level, c, confidence interval for p is p hat plus or minus our critical z, and it is z because we're back to a normal distribution. We don't need to use a student's t for this. 1 minus p hat over the square root of n, where z star is our critical z for the standard normal density curve, with the area c being between negative z critical and positive z critical. So remember, it's like z star for a 90% confidence interval is 1.645. For 95%, it's like 1.96. And I'm pretty sure for 99%, it's like 2.33 or 2.23. It's something similar to that. Those are our critical t's. And we can use this interval only when the number of successes and the number of failures in the sample are both at least 15, right? We need a sample size of at least 30. So how can I choose my sample size? Well, the margin of error in the large sample confidence interval for p hat is going to be z critical times p hat times 1 minus p over n, and then you take the square root of that, where z star is the standard normal critical value for the level of confidence we want, right? If we want a really small margin of error, we're going to need a much bigger sample. So the level C confidence interval for a population proportion P will have to have a margin of error approximately equal to a specific value of m. So like this tells us our m, but if we want to pick our m, we need to pick a bigger sample size. So we're going to take our z critical divided by m times p star times 1 minus p star, where p star is a guessed value for our sample proportion, right? The margin of error will always be less than or equal to m if we take our p star to be 0.5. Right, so like 50%, like guessing. You can do a better guess if you kind of know it, like have a gut instinct or have some preliminary examples. But you always want to pick, you can use this formula to pick your sample size. So let's conduct a significance test for this proportion and find a +4 confidence interval. So significant tests for a proportion are pretty much the same as for a mean. It fits a normal distribution. So I want to test my hypothesis that P equals P naught, where Z is P hat minus P hat naught over P naught times 1 minus P naught divided by N. And in terms of our variable Z having the standard normal distribution, the approximate p-value for a test of H naught against is P is equal P naught than greater than Z is greater than Z. P is less than, so Z will be less than Z. And P is not equal to, so P would be Z, which is greater than or equal to the absolute value of Z. And we have to use this test when the sample size n is so large that both n p0 and n times 1 minus p0 are 10 or more. So the sample size kind of depends on what your probability is. So the confidence interval p hat plus or minus c critical times p hat times 1 minus p hat divided by n for a sample proportion p is easy to calculate and understand because it's based directly on the approximate normal distribution, which is really nice. But unfortunately, confidence levels from this interval are often inaccurate for proportions unless our sample's very large. So the absolute confidence level is usually less than the confidence level you asked for in choosing your Z critical, right? Because we choose our Z critical based on what confidence interval we want. But there is a simple modification that works to improve the accuracy of our confidence interval. And we call it the +4 method. Because all you need to do is add 4 imaginary observations with 2 successes and 2 failures. So I have P, I think that's supposed to be a tilde. I don't know why I gave us a percentage. P tilde is the number of successes in the sample plus 2, that's our adjusted, and the number is total number in the sample plus 4, right? This helps us correct and make our confidence interval more accurate. So using the +4 method of P, we have the number of successes plus 2 over n plus 4, and a +4 confidence interval for a proportion. All these percentage signs, they're tildes. I don't know why they're showing up like this. So to get the +4 confidence interval for P, you add 4 imaginary observations, 2 successes and 2 failures. So your new sample size is n plus 4, and your new number of successes is adding 2. So you have P tilde plus or minus Z times P tilde times, which is our adjusted P, times 1 minus P tilde over n plus 4. And we can use this interval when the confidence level is at least 90% and n is at least 10 with any counts of successes and failures. And this makes it more accurate and more applicable because we can use it for a little bit of a smaller sample size.